This is a brief introduction to the problem statement for non-invasive blood glucose monitor for neonates. The normal levels of glucose in blood in humans are in the range 80 to 120, and in diabetics they may be much higher or lower. Neonates are babies less than 1 month old, and neonates born to diabetic mothers have to be monitored for concentration of glucose in blood every 4 hours. The current methods for measurement of glucose in blood are invasive or minimally invasive, and they can lead to trauma. So we would prefer to have methods that are non-invasive. Non-invasive means that you do not puncture the skin. A device for non-invasive measurement of glucose in blood is expected to have these elements. A sensing element is required that can give a signal proportional to the concentration of glucose in blood. A transducer will convert that signal into an electrical signal. That signal may have to be amplified if it is weak, and then it has to be digitized so that it can be recorded, transmitted, or displayed. Although we require the concentration of glucose in blood, it is not necessary that you make the measurement directly in blood. Other body fluids such as sweat, tears, interstitial fluid, and saliva may serve as proxies. That is, if the concentration in these body fluids has a high correlation with the concentration of glucose in blood, and you can compensate for the confounding factors. A variety of methods have been suggested and tested for measurement of glucose in blood non-invasively. A brief list is shown here. Sonophoresis or iontophoresis can be used to extract interstitial fluid, and the glucose in the interstitial fluid can be measured using electrochemical methods. The chemical composition of breath can be analyzed for compounds such as acetone, which have correlation with blood glucose levels. Or scattering of electromagnetic radiation can be measured using reflectance, interference, or transmission measurements. Or absorption of electromagnetic radiation can be used to measure glucose concentration. Glucose is optically active, so it rotates the plane of polarization, and higher concentration of glucose lead to greater rotation of the plane of polarization. Fluorescence and Raman spectroscopy measurements are more specific, but also more and the sensitivity is lower, so more difficult to make. So the instrumentation will be a little bit more complicated than absorption, polarization, or scattering based methods. Microwave based resonators and bioimpedance measurements have also been used for measurement of glucose in blood non-invasively. Photoacoustic and photothermal methods use a beam of radiation, usually a laser, and it's absorbed by glucose. The resulting sound waves or heat are measured to estimate glucose. Now there are at least 10 publications on each of these methods, and in some cases more than 100 publications. However, there are certain problems with most of these methods that prevent clinical translation, such as problems with linearity, precision, accuracy, and some of these are subject to variation due to temperature, humidity, hematocrit, or oxygen. They may be subject to interference from vibration or electromagnetic interference from, say, cell phones. Some of these devices may require frequent recalibration because the signal varies as a function of time, and some of them may produce adverse effect. So although there are many methods that are potential, it is there is still a requirement to close the gap between the technological capability and the clinical application. And the objective of this competition is that you can make that leap by improving either the hardware of this or the software, so that the gap between the current technological capability and clinical requirements are closed. For a device that is appropriate for clinical applications, most of the measurements will have to be in the A or B parts of the Clark error grid. If the measurement has less than 20% deviation from reference value, it is in A part of the grid. If the deviation is more, but it would lead to benign decisions or no treatment, it is in part B. So A plus B should be, most of the measurement should be in A plus B range. Examples of devices that are commercially available are shown here briefly. One is the glucose watch biographer that uses reverse iontophoresis to extract interstitial fluid into hydrogel discs, and the glucose there is oxidized, and the hydrogen peroxide produced in the oxidation process is electrochemically measured, and the electrochemical signal is converted into blood sugar level. This device has been approved for adults more than 18 years, not for neonates. These are the properties of this device. It has good linearity, precision, accuracy. However, in 2007 it was discontinued because 1 to 2% of people who were using this device experienced certain adverse effects. The technology described earlier has been improved in the device known as SugarPeat, which has been approved in EU but not yet in the US. It's based upon the same method, reverse iontophoresis, for extracting interstitial fluid. These are some minimally invasive devices. As we said, minimally invasive devices will not qualify for this competition. However, these are commercially available. This Freestyle Libre is approved for adults, also for 4 to 17 years old, and the Dexcom G6 or G7 is approved for greater than 2 years old. However, none of these is yet approved for neonates. A device known as GlucoTrack is marketed in EU, has not yet been approved in the US. It uses a combination of ultrasonic, electromagnetic, and thermal waves. It's a clip-on sensor which can be clipped onto the ear, and the data is sent to a smartphone. D-Base is a device being developed by Diamantech. It is approved in the EU for clinical trials, not yet in the market. It uses an infrared laser beam that passes through the skin of a finger. Glucose converts the light in the laser beam to heat, and the increase in temperature is measured by the device. This is a reference that summarizes the information regarding many devices that have been developed and tested. And I hope that this introduction helps you to develop a device that will close the gap between the current technology and the requirements of clinical application. Thank you.